So the last lecture we looked at contour lines, and today my plan for the first part before the break, we have to finish this presentation here. And after the break, we will do a civil 3D training on the same subject, which is contour lines, and we'll see how we can create contour lines and other things on civil 3D. Just before I start, I want to make sure that every one of you guys are aware of the resources available for you. You have videos that is being recorded every class, and those videos are then placed into a channel. The channel is on MS Teams. The channel will have all the videos, and I always go ahead and rename the videos according to the week and the lecture and the part number. So you should be able to kind of find a sequence. In addition to the videos, there are some other ways or resources which is available on the D2L where you can find a presentation, like for example, this one you can see on my screen, in addition to the civil 3D tutorials, which also shows you how to do some skills on civil 3D. Please download them, read them, and if you see any way of improving them, if you have some comments, please feel free to share your comments and concern with me. Okay, so today I'm going to start right now again one more time on contour lines. So in the last class, we looked at contour lines as a way of for us to read and interpret and recognize the topography, because you know that the first step to perform several tasks on like on any project, you need to understand the topography. For example, one of the very clear example is designing a road. So designing a road and selecting the route of the road, you need to look at the topography, because you have to look at the contour lines, and you try to avoid areas where you have steep slope and go on areas where you have a mild to low slope, so you minimize the amount of cut and fill. So we looked at this example last class where I'm showing you a part of a contour map. We're able on this map to figure out where are the areas that has the highest slope. If you guys remember this area here, because contour lines are very close to each other, and that's why this area here has the highest slope. Again, if you look at, for example, this area looks like it's kind of a mild slope. So that's one thing. The other thing that we mentioned also last class, that we do not label all the contour lines. There are some contour lines in this picture, it is being labeled, like for example, the 850 and also another 875. And in between there is 1, 2, 3, and then 4. 4 contour lines are unlabeled, and only the fifth contour is labeled. So we label every fifth contour line. And if you guys remember, we call those ones that we label major or index contour, and the ones that we leave unlabeled in between called minor contour lines. Now let me ask you, anybody can look up my screen and tell me what is the contour interval for this map?
5 meters.
Thank you, sir, so much. Please, it is not 25 meter. The contour interval is not 25 meter. It is 5 meter, because yes, the difference between the 875 and 850 is 25 meter. However, you can see I'm cutting the ground every 5 meter. So basically this is 855, 860, 65, and then 70. So the contour interval for this map is 5 meter. Please remember, contour interval must stay and remain constant within the entire map. For example, we cannot, on the same map, we cannot use interval every 5 meters some areas, and some other areas we do 1 meter. Otherwise, there is no way for you to understand the ground. So the contour interval must be constant within the same map. Yes, if we create another map with a different scale or different area, maybe we can use another interval. Also, something I wanna remind you that we label the major contours and we don't label the minor contour. However, also we will need at some point, we need to clarify any confusion by adding something called spot elevation. Spot elevation. Spot elevation is just only one point. We place the elevation and this will simply eliminate any confusion. For example, you can see here my ground went from 875 going up to 900. Here it's 900 here, but to be honest, if I hide for you guys, if I hide this number, I'm not sure if I can hide it. Yeah, if I hide this number and I hide also this number, okay? So I'm hiding those two numbers just to show you their importance. Can anybody, if I hide those numbers, anybody can tell whether the ground will keep up, going up or goes down again? We don't know. So to remove the confusion, if we place one of those spot elevation and remove and then also place the spot elevation, right away you will know that my ground is still going up because this contour line here is 905 and this one is 910, and then you can see the elevation here is 912. So my ground kept going up in this direction, this direction. Also, we do this. So this is a called summit, and we do this also in depression. I know that my drawing here is missing something, so you need to understand that we need to place here an elevation where the user of this map will know the ground, whether it's going up or going down in this area, okay? Um, so guys need to remind you that contour lines, they have properties, and through their properties, we can interpret them. So for example, contour lines are closed lines. And I know some of you will say, oh, Tahir, stop, wait, watch this. So yes, this is a closed line. This is also a closed line. But some of you will say, how about these lines here? These lines are looks like they are open. Anybody has a clue? Although I said all the contour lines are closed, why those contour lines they are not closed? Okay, maybe it's a difficult question. Here is the point. The point is what you see here is a contour line for one area. It means my survey on this side here, I have no survey, but I have survey here. So I have elevation data on the right side, but not on the left side. So there is no data, and that's why all my contour line, they stopped here. They have been trimmed here. But if you were to continue and survey the entire area, I promise you the contour lines, every single contour line will have to close at some point, whether within my map or outside my map. So contour lines, all of them, they are closed line. And the distance between them tells you about the slope. When the distance is so close, then it is very steep slope. Okay. Also, contour lines in general, they never meet. They never meet, they never intersect, except for very, very few and rare situation. I give you here three examples. If you have a contour lines intersecting with wall or cliff or cave, then in these cases, your contour line will intersect. So in general, those are very rare, like walls and cliff. Cliff, it means it's a vertical side, and cave, there is a kind of a caved area into your mass, and that's why those are very rare. In 99%, you won't see any contour lines that they are intersecting or even tangent to each other. Okay, now you guys understand we just talked about the contour interval, and if you don't know what a contour interval is, let me remind you. So here is this picture here, and this distance, which is the vertical distance between those virtual planes that we're cutting through our ground. Remember those red 1, 2, and then 3 and 4 and 5, those are horizontal planes which we cut our ground with. The vertical distance is what we call it a contour interval, which is in this case was 1 meter. The choice of the contour interval has two main factors. When we choose them, there are mainly two factors. Number one is the nature of the terrain. You guys can imagine if I go to soccer field, which is pretty much flat, should I use 1 meter contour interval? I'm asking you, what do you think? In a room or maybe a soccer field, something that pretty much flat. Would you use a big contour interval or a small contour interval?
Big contour interval?
If you choose, for example, let's say in your room, you have a 1 meter interval. Your room already, the difference between elevation at every corner of your room, probably 1 or 2 centimeters, which means if you choose 1 meter interval in your room or something that is flat like a table or maybe soccer field, it means you will not see any contour line. When things are flat, we simply make our contour interval smaller so we can get some contour lines. On the opposite, what if I'm trying to make a contour map for area which is a mountain area? Okay, an area that has mountain, for example, like Banff. Please do the following. Think about it. What if we're creating a contour, a map for Banff with an interval of 1 centimeter? What is going to happen? Any help?
You're
So
gonna
I'm
have too many
cutting the
lines.
ground in. So excuse me. Keep going, please.
You're just gonna have too many lines. It's gonna be too cluttered.
Yeah, exactly. So there will be too many lines to the point it will be like a spaghetti, like black. You won't see anything. And that's why for mountain area, we increase the contour interval. We cut our ground less frequently, so at a very large interval. The other factor that controls the selection of your interval or contour interval is the map scale. Because simply we can make a map for one community, or we can make a map for Calgary, or can make a map for Alberta, or maybe a map for Canada. Remember, when we make a map for community, we use a large scale. When we make a map for Alberta, we need to fit a bigger area on a smaller size paper, so we use a smaller scale. Remember, 1 over 10,000 is a smaller than 1 over 1,000, okay? The second factor that controls the contour interval is the map scale. So in this slide here, I found a table that kind of relates the interval of the contour to the type of the terrain, also to the map scale. So for example, if you're producing a large scale map, which is 1 to 1200, okay, or larger, for flat, you're going to use between zero point 0.5 to 1 feet. So this is metric. It's about 0.15 centimeter to 30 centimeter. Let's go to the other extreme. If I'm creating a map and the scale is 1 to 12,000 or smaller, and the ground is mountain, in this case, you're going to use a 50 feet or 100 feet. 100 feet is simply 30-meter vertical spacing between those virtual planes. Okay. Now, there is also one topic here which I'm going to touch on today, but you will know more on one of them today, but we will continue discussion throughout the whole course about these models. So the thing is, now when we spend some time on site and we do the survey using Total Station, our final product will be discrete points, maybe 1,000 points of known easting, northing elevation. However, we can, for example, copy this file into our machine. Then we are going to use a software to store the information of the elevation on our computer. And that's why there is a discussion here about elevation models. Look at this name, elevation model. The discrete point is not a model, it's just a discrete point. You will know better during this class about something called TIN and what does it mean, elevation model. But for now, here are two models that we use to store our elevation data. Number one is we store the elevation data in a sort of array or a matrix of a given size. So for example, I will know the elevation of, here, and I will know the elevation here, and I will know the elevation here, and so on and so forth. So that's called the digital elevation model, or we call it DEM. We will go to this one later in this course, so you will get more information, not today, but during the course. However, really the one you will have more information is today is about the second one. So in today's class, after the break, you will see I will give you more information about 10. So what is 10? 10 is something called a triangulated irregular network. And I know by now this didn't add anything to your knowledge right now. So what does it mean? I don't know anything about it, okay? So anyway, so for now, you can imagine that these points here, like this point here, and this point here, and this point here, those are measurement of total station. And the computer will simply connect these points by a triangular face, and it keeps doing this over and over and over, so it ends up with a network of triangles. And that's why it's called triangulated irregular network. You will get more details about this model today in the Civil 3D portion. Okay, so you can see here, I tried to show you kind of visualization of what is 10 and what is DEM for now. To do that, what I did is we have a data for SAIT. So the picture on the right, this is the southeast corner of SAIT, where this is the soccer field. This box here is the soccer field, and this is the 10th Street coming from downtown to 16th Avenue. Also, this is the parking area at the back of SAIT, if you guys still remember. Okay, so what I did here is I took this area and I zoom in to show you what is 10. Watch this, please. So as I said, at every one of these nodes, there is a survey point. And what we do is we connected the 3 points by a triangular face to create a continuous model of elevation. So the building block here is a triangle, and that's why we call it 10. Now, the other model that we can store our elevation data, which is not 10, called DEM, or digital elevation model. In this case, the building block, it is not a triangle. The building block is square or pixel. And that's not new. If you guys take any digital image like you have captured with your own camera, you will see the smallest element on an image is called the pixel. The thing here is different. In a real image, simply we store colors, like for example, something like red and green and landscape. However, in DEM, we don't store true colors. We store elevation. And what this means, look at this place. So as I said this again one more time, the southeast corner of SAIT, where this part here is the soccer field, and this thing here, it is 10th Street, coming from downtown on the south to the 16th Avenue on the north. Now I took one area here and I make a zoom in. So let's zoom in and see. So what happens here is simply there is a building block, which is a pixel. So this pixel here, it has a color. And this color, it ranges from black. And you need to look at the legend here. So it ranges from black to white. White means highest elevation of 1091.21. And black, it means lowest elevation, which is 1051. So you can see the DEM is simply an array or matrix of number where every number is the height of the area, okay, or the pixel, and represented in color. Light color or white color, it means high. For example, the soccer field is very high or the highest elevation, while this area here, it's in black, which is the lowest elevation. Now, this part here, it shows you, my intention for this part is to show you how do we generate contour lines manually. How do we generate lines manually? Okay, so, you know, in general, we have so many points. Like when we do the survey, maybe we have 100 point, 200 point, 1,000 point. In this example here, I'm not really showing you the 1,000 point because it's almost impossible to understand. So what I did is I just took only 4 points, only 4 points. What are those 4 points? You can see them here. Point A, B, C, and then D, where we measured the elevation of these points. Okay, the elevation of these points are in red, like 20.3, 21.4, and so on and so forth. And what you see here, I'm gonna make it a box. I make a mock box here so you guys can follow me. So what you see here is a plan view. Please understand that this is a plan view. So we're looking from things from up down. And we see 4 points of non-elevation. One more thing is the spacing between the points is 20 meter by 20 meter. Here is the 20 meter and here is the 20 meter. Those are the X and Y spacing between the point that I measure elevation for. Now, ultimately, if I'm able to locate contour points, where are these points? I can simply join them and create my contour line. In this example here, I'm not going to find all the contour lines. I will only focus to show you how this done. I will try to locate contour line 21. Please watch this, huh? So I'm trying to locate or draw contour line 21 only. Remember, by definition, when we say contour 21, it means by definition, it's a line connecting all the points of the same elevation of 21. You guys agree? When I say contour line 21, it means this line connects all the points that has elevation 21. That's by definition of contour line. So what happens here is, you can see I gave you here 4 different elevations, 20.3, 20.15, 21.95, and finally 21.4. And now our job is to say, do we have points of elevation 21 in this area? Let's see. Please help me if you can. I'm asking you, is there any point along the line AC that has elevation 21?
No.
No, thank you, sir. That's correct. So there is no point here along this side that has elevation 21. Let's do it one more time. Do we have a point here anywhere between B and C that has elevation 21?
No.
No. Okay, so now let's do the exercise third time. Do we have elevation here, any point along the line AB that has elevation 21? Look at the numbers. So my ground here is climbing from 20.3, climbing up to 21.4. So my question for you is, along the way, as we climb from 20.3, going up to 21.4, assuming that it's line, it's a linear relationship, are we going to find any point or meet any point with elevation 21?
Yes.
Yes.
Thank you. Yes. So along the line AB, yes, there is a 21 elevation. The question is, let me give you some example. Is it here? Or is it here? Or is it here? Do we know now without any calculation?
No
You could
calculation.
approximate, but you should probably do the math.
No, I'm referring to the exact location of the point that has elevation 21. My question is very simple. Are we sure is whether it's here or there, or we have to find out where this point is?
You have to find out where it is.
Exactly, sir. So what we have to do is, please watch this, so you can see, I know, yes, there is a point here, but I don't know exactly where this point is. And that's why what I will do is, I'll go here and I'll say, you know what? I don't know. And you guys know, when I don't know, I call this one X. Okay, so I don't know where the point that has elevation 21. So I'll call this one X. By the same token, if you think about between C and D, where is this point that has elevation 21? Also, you will see, yes, we do have a point that has elevation 21 as we climb from 20.15 up to 20.95. Yes, we do have a point somewhere here that has elevation 21, but also we don't know where this point is. And that's why, because we don't know, then I will call this, I will base a point here, and I will call, you know what, let's call this one another X, because we don't know. Now, really, my job is this. If I'm able to mathematically find how much this X, then problem solved. Because if I know where this point exactly, then I know that this point is 21 and this point is 21. Then where is my contour line? My contour line in this square is just go from here to there. And remember, I'm just giving you a small sample, because otherwise there is no way for you to understand. I'm showing you only one square. But if I give you 4 squares or 4 cells, It just takes more time because you have to solve for x so many times more, and then you will have to continue drawing your contour line. Okay, so really, my like the remaining parts going forward is I wanna go from a plan view that contains spot elevation, which is A and B and C and D, to this picture on the left. And this picture on the left, you can see I do have a contour line, which is contour line 21 here. How to do that? I think some of you already figured it out. You can see how can I find the x, this x and this x? We need to do a linear interpolation. Linear interpolation. This is how we find this x and this x. I'm gonna show you in more details how can we find the x. Please watch this. To do that, and remember, what you see here and there, both of them are plan views. Plan views. So we're looking from up, down. In order for us to do linear interpolation and for you to better visualize, we need to look from the side view. So I have to look between A and B from this direction, and I have to repeat the same thing. I need to look between C and D from this direction. So I need a side view. Let's start. So here is the side view, and I call it here elevation view between, I'm going to start here between line AB. You can see between line AB. And what is given? Look at this. What's given? What's given is the elevation of point A is 20.3, and the elevation of point B is 21.4, and the distance in between is 20 meters. What is the question? The question is, where is the point of elevation 21? So this is given like numbers. How about graphics? This is even better. So you can see the elevation of point A is 20.3, while the elevation of point B is 21.4. And really, what is my target? Here's my target. I'm after this. I want to find where is X for a point, which is point number 1, that we know that the elevation is 21, because I'm trying to draw a contour line 21. Okay? So really, this is my target. I want to find X, which is not really very difficult process. Let's work the math out. Let me show you. So between A and B, this dimension here, this dimension from A to B, remember that this is elevation view. So we don't see easting, northing, we see only elevations. So this is very simple. This number is 21.4, which is the elevation of point B, minus 20.3, which is the elevation of point A. And what do we get? We get 1.1. So this side here of the triangle is 1.1. And if the elevation of point 1 that we're trying to find, we know the elevation is 21, and the elevation of point A is 20.3, so we know that the difference in elevation is 0.7, which is 21 minus 20.3. Now, it will become very, very, very easy because we have two similar triangles. This smaller triangle is similar with the big triangle. What does it mean? It means x, or sorry, 0.7 over x. This side over this side is equal to 1.1 over the base, which is 20 meters. And finally, we end up with this equation. 0.7 divided by 0.7 divided by x equals 1.1 divided by 20. This is similarity of triangles. Now, when you solve this simple equation, what you will get is you will get 12.727 meters. Remember that the x is measured from point A. According to this math, my x is measured from point A. And again, we're done because simply I can come here, I can edit this number, I can say my point is 12.727. I found out where is my point 1. So this is point 1. You need to do the same thing one more time to locate where is point 2. But before I do that, I want to mention something. If you do that on AutoCAD, where we have no scale, remember in AutoCAD, that's something I guess we agree last time, that when we draw things in AutoCAD, we don't scale it down or up. We just use the normal units, like for example, 12 meter or 20 meter. The scale is only when we print maps, okay? When we print maps or block maps, so then we need a scale because we don't have a paper size that matches the reality. So that's why we need to scale things down. Now I'm asking you here, remember that this is in meters, 12.727. So on site, the point that has elevation 21 is 12.7 meter from point A. Now let me ask you, what if you draw this on a piece of paper with a scale? For example, you already draw the grid lines here. So we have grid lines, and the grid lines, yes, in reality, the grid lines, the spacing is 20 by 20. However, this is already placed on a piece of paper. So we scale this one down already. For example, let's say I use a scale 1 to 1,000. So the scale is 1 to 1,000. Okay. And what does it mean 1 to 1,000? I know that some of you even now they struggle with this 1 to 1,000. It means a 1 centimeter on my map represents 1,000 centimeter on site, which means in simple English, 1 centimeter will represent 10 meters. 1 centimeter on my map represents 10 meters on site. And guess what? It means when I draw this grid line on my map, looks like I have to present them as 2 centimeters. Why? Because a 1 centimeter is 10 meters, so 2 centimeters, which is 20 meters, and the spacing is 20 meters here. Now, let me ask you, you want to draw your contour map. How can you plot your point 1 on this grid line here? Okay, so I have my grid line here, and this is point A. So my point A is here, my point B is here. And from math, I already found out that I have a point here in between A and B, and it's away from point A by 12.727. Now, can I put here 12.77, or I have to convert my 12.727 to the scale? I'm asking you.
Convert it to the scale given.
You have to convert it, and when you work the math out, you will see this will be about 1.27, and I think that's enough centimeter, huh? So because this is already to scale. If you do it on AutoCAD, no need, huh? If you already draw the grid line on AutoCAD, then you need to make an offset of 12.727. If you do it on a piece of paper that is already drawn to a scale, then you must convert. I'll give you a trick that will save you some time. Guys, what if I come here and I cross this 20 meter and I write here 2 centimeter? Any help? Can I do that? I do the same math, but I replace the 20 meter by 2 centimeter, which is a great size after the scale. My X will be right away in what? What would be the units of my X?
Divide by
Centimeter.
Will be right away in centimeters, so you don't have to waste your time and do one more time. So you can do the math based on actual dimension or based on your grid size after the scale. So it's up to you. You can do it on 2 steps. I know that this is clear, huh? So that's 20 meters on site. I need to find where is point number 1, then scale it down. But you can also save some math by replacing the 20 meter, which is on reality. And if you take the scale into consideration, so this is equivalent to 2 centimeter. So your X here will be right away in centimeter, which you can take right away and plot it on your map. Hopefully this helps. Okay, now let's do one more time, which is, look at this please. I still need to figure out where is point 2. Where is point 2? To do so, I need to look from the side view, okay, from this direction, and draw point C and D on the side view and try to locate point 2. This is another time to do it just in case if you couldn't capture the first one. Please watch this. So what do I know? I know that the elevation of point C is 20.15. H of D is 21.95. The horizontal distance is 20 meters. What is my job? I want to find where is the point that has elevation 21, which is the contour line number, okay? Which is point number 2, huh? Then again, in graphics, here is elevation of point C, here is the elevation of point D, and here is the elevation of point 221. Then the same thing, huh? You need to find 1.8, which is not super science. It is the elevation of point D minus elevation of point C. And also you need to find this distance here, which is very simple. It is 21, which is the elevation of the contour, minus point C, which is 0.85. Then do similarity of triangle, where you say my 0.85 divide by x equal to 1.8 divide by 20, or so you get 9.44, or you can replace your 20 based on how much it will be on your map depending on the scale. Okay. Any questions so far? So I want you to imagine that I didn't show you the whole process. I showed you how to do linear interpolation. However, you need to imagine, what if I give you more data? For example, let's say I give you another square here of known corner elevation. So I give you the elevation at this corner as well, and the elevation of this corner as well. You know what's going to happen? What's going to happen is you need to keep going. You need to find out. For example, let's say I give you elevation here is equal to, let's say, 21.60. So what you have to do is you say, you know what, I do have a point here somewhere in between that has elevation 21. I do linear interpolation, and finally I'm going to say, you know what, here is the point that has elevation 21. In terms of contour lines, you need to go connect point number 2 to point number 3. Hopefully you guys get the idea, huh? So if I give you more data, which nothing more than you need more time to do that, you should be able to continue and finish your contour line. This is exactly how the software will do it, and but for sure it will do it faster than how you do it. Okay, now I want you guys to watch on this slide here, and that's the last slide before we take a break and we come back for about 50 minutes on Civil 3D. So what you see here is not really, like, remember, I give you only one square. So in the previous exercise, I gave you only this square, 4 points of known elevation, and you want to interpolate on maybe one side or 2 sides or 3 sides to find the contour points. The thing here is that this is just more work, huh? More work. So we have more cells and we need to do more linear interpolation. However, I want to mention something, that this map has been created using Civil 3D. Civil 3D. And let me show you the difference, huh? So the difference is, if you guys remember, 5 minutes ago, we were trying to find a point that has elevation 8, okay? Elevation 8. So using linear interpolation. And also we go to this side and we try to find elevation that has a point that has elevation 8. So what's next? What's next is we go ahead and connect these 2 points together, and this will give us a piece of contour line 8. If you agree, let's make it different line type. Now, what you see here, do you see something that's different? Anybody can see a difference between what we do manually and what the software does manually? I'm sorry, what the software does? Do you see any difference?
It does the diagonals too.
Okay, great. Thank you so much. You kind of saved my time. I was trying to say, you know what, my contour line did not go straight from those interpolated points, rather than you have here a little bit kick here, okay? So it's kicked here. Now, you already figured it out because you guys mentioned about the diagonal, huh? And the diagonal is the secret. So the software has done extra effort by interpolating and trying to find where is the point that has elevation 8 also along the diagonal. So simply figure out a third point here. And that's why what it did is simply connected the line from here to there and then from there to there. So my question for you is, which one you think it's better contour line? The one we have done manually or the software?
Software.
The software for sure, because simply it did extra effort and come up with a refined shape of your contour line. For example, look at this. Look at this. This is very extreme, huh? So the software here, if we do it manually, we're going to go ahead from this point to this point right away. While the software, based on the interpolating along the diagonal, it came up with this point where the contour line has been, broken this way. Okay, has been broken this way. And you can see there is a huge difference between the manual contour line and the contour line drawn by the software. Now, some of you will say, okay, Tahir, great. It means we can do that. We can do same job at the software. So what we do is we simply connect the diagonals, like those blue lines, and we can do extra effort and we can interpolate along diagonals. Then we can come up with a better contour line or refined contour line. You guys agree or disagree?
Agree.
Yeah, agree. However, the tricky part is those those diagonal lines are just a random line. Look at this. Some of them, they're going this way, and some of them are going this way. You guys see it? Some of diagonal lines, they are not really always going from the northeast to the southwest. No, they can take any direction. And remember, I'm asking you, both of them, they are correct. For example, if I come here and I draw a diagonal from this point to this point, and let's say I give it a dashed color or dashed line, I'm asking you, now we have two diagonals. One is in blue and the other one is in red. My question is, what do you think? You think of those that it can be any one of them, so anyone can work, so I interpolate along any one, or no, one diagonal is right and the other one is wrong? Any guess?
Wouldn't you want the one perpendicular to the first line you drew? Like it doesn't really work in that. Sorry, go ahead, Luca.
Perpendicular to what?
Well, when I saw like the green line drawn, wouldn't you want to draw your diagonal perpendicular to that green line? So when you interpolate.
Remember, sir, that the green line is a byproduct. So the green line comes after you pick one of the diagonals. So it's not like you have the green line and you can come up with a diagonal. It's the opposite. You come up with one diagonal along which you interpolate, then you can find the green line, which is the contour line. So the contour line is a byproduct of establishing one diagonal. My question is, I'm gonna say my question one more time. Now you have this square. Is like, are both solutions are correct? Like, should we interpolate along blue or red, or it doesn't matter? We can do either one of them.
Is that in the quadrant? The elevations are very close, 1023, 1022. So it's kind of a flat. That's why there is not a diagonal.
So in general, here's my response. In general, although it looks very trivial, like, pick one of the diagonal, it doesn't matter. No, it matters, because really the grounds could be one or the other, but it cannot be both. Remember, your ground here is folded, and it's folded either around this diagonal here or folded around this diagonal here. It cannot be both. It can be folded around either the blue or the red, but not both. So the hard question, which is you don't know how much mathematically involved to decide whether the blue or the red, this is a whole story. And it looks like very simple to you. Like, why don't you choose one of them, not the other one? The software will have to do a lot of calculation to decide whether the ground is folded around the blue or folded around the red. Okay? And we're not going to go into this business. If I ask you to draw contour line manually, then what you have to do is just interpolate along the sides of the square, and then you don't have to come up with a refined or the best shape of the contour lines. I want you to understand that the software will do a refined shape of contour lines based on the interpolation on the diagonal, and this process is not easy. Mathematically, to say this diagonal is the right one and my ground is folded around this diagonal here, not the opposite, this is a very mathematically involved problem. And if you are interested, it is called the Delaunay problem. And this is a long ever problem, and mathematicians, they figure it out, and they come up with optimization software that trying to minimize the surface area of those triangles. And that's why, please forget it, huh? We will leave the software to do that. If I ask you to draw as a test or as a training for you to draw one on contour lines, do not interpolate along diagonal, just interpolate along the sides of the square. Okay, but you need to understand that software interpolates also along diagonal, which is hard to find. Any question for now? Okay, so guys, so I need just to give you a summary of what you've learned so far, and then we take 10 minutes a break. So we started our presentation last class by teaching you what is a contour line and what are the properties of the contour lines. And also we talked about contour interval. We talked about elevation models, but I know 100% that you guys are not following 100%. What did I mean by this? Please wait until after the break, and I'll give you more information about this tin model. Okay, we also looked visually at what tin model looks like and what is GEM looks like, and both of them, they give you, or we can store elevation data of the same area, but using two different techniques. Okay, and then finally, we looked at how can we draw contour lines manually. And then we also looked at how the software will do it. And we talked about those diagonals. After the break, we will take 10 minutes to break. Please, when you come back, get ready with your Civil 3D. Thank you so much. And I will have, excuse me?
Sorry, I have a quick question for assignment 2. For the dimensions of the building, do you want the lines read or the dimensions read, or both of them?
I mean, I'm gonna review the text, but here is a general something for you. Like, if I am not specific about a requirement, please don't ask me. It means I leave it up to you. Okay. So probably you have a valid question. Probably I'll have to go and check. Okay. But probably I'm looking at the text to be read. But for example, if I don't say, for example, the size of your the size of the arrow, don't ask me what the size of the arrow. It means I leave it up to your choice.
Okay. Thanks.
No problem. Okay, so you guys, will see you in 10 minutes. We'll see you back here at 12:57.